Hi everyone, this video is about something called Lagrange multipliers. Lagrange multipliers gives us a strategy for finding the global max and global min of a function. A alternative strategy based on finding local max and local min of a multivariable function was already explored when we talked about the method where we take partial derivatives with respect to x and y, set them equal to 0, solve for all the critical points, and then diagnose those critical points as max, min, or saddle using the diagnostic function capital D of x comma y. So to give a more concrete description of what the difference is between local and global maxima and minima, consider the idea of looking for the tallest mountain, or all the mountains, or all the tops of all the hills, anywhere. So you head off in all directions looking for anything that looks like the hill, anything that looks like a mountain. A different question would be, what is the highest point 5 kilometers from here? So that question could be answered by looking at all the hills and all the mountains 5 kilometers from where you're standing, and then comparing them all. But what that method might miss is it might miss that the highest elevation is occurring at the 5 kilometer mark. So to draw a kind of a silly picture, if you're standing here and there's let's say you're on a kind of hill, it goes down and goes back up to a taller hill, right? And then it goes like this. Maybe it does some more interesting stuff over on the right hand side. And maybe that distance from here to here, maybe that's 5 kilometers. So what's the highest elevation 5 kilometers from you? It's not the top of a hill, it's the boundary, it's the 5 kilometer mark. If you went further, yeah, it goes higher, but that wasn't the question. The question was 5 kilometers from where I am now, what's the highest point? And that's really the crux of what constrained optimization is doing, or at least this type of constrained optimization that we're going to talk about. It's looking for the maximum of a function on a boundary, or the minimum of a function on a boundary. We can explore this type of maximization and minimization process with the fence problem, a classic fence problem with the farmer. Farmer has 60 meters of fencing, wants to build a rectangular fence along a very long barn, so the farmer can use that barn one side as free fencing. That's one way to think about this. We would set this up previously in single variable calculus as an area is equal to a length times a width. So if I label the lengths and widths x and y, our area will be x times y. This is a 2D function of two variables. And we could do multivariable optimization the same way we already did. We take the x derivative, we get y. We take the y derivative, we get x, set them to 0. On one solution, 0, 0 is our critical number. Then we construct the capital D function. We find the capital D function is equal to -1. So all of our critical points are, capital D function is equal to, -1. So we end up with a saddle point. We don't end up with anything particularly interesting happening. What we need to do is we need to build in the additional information. We need to build in the constraint. The reason we're not finding a global max using that strategy is that if we don't put a constraint in place, there is no global max. If you have infinite fencing, let x equal infinity and let y equal infinity. You can make the area as large as you want. It's really the constraint, the limited resource, that gives this question any type of meaning. Or the reason it's not finding a minimum is because we haven't set up that x and y are forced to be positive. So the minimum area would be a negative area. So we really do need to carefully describe the physical features of our problem inside the mathematical model if we want a mathematical model to give us an accurate output. Okay, so we make the assumption that the farmer is going to use all the fencing. So we would say that all 3 of the sides that we're going to fence, so the x plus the y plus the other x, is going to add up to the 60 meters of fencing. We'd simplify 2x plus y is equal to 60. And that is our constraint. I'm going to give it that name right now because we're going to start using that name on a regular basis from here on in. So our constraint. And that constraint gives us a connection between the variables x and y. What we did previously was we rewrote our constraint by isolating for one of the variables. In this case, it's easiest to isolate for y. And then we use that to rewrite this function to just be a function of x times 60 minus 2x. And then we could use our methods from single variable calculus to optimize. So we would take the first derivative. We only have one variable, so there's only one first derivative, it's just f prime. We get 60 minus 4x. We're looking for critical points, so we're looking for where the slope of the tangent line is horizontal. So we're looking for the derivative is 0. So we set it equal to 0. So 60 is equal to 4x. Divide both sides by 4, we get x is equal to 15. Then we could go back and find the y value. Y is equal to 60 minus 2 times 15, which is 30. So our max area, if x comma y is equal to 15 comma 30. And we would also done a check. We would have checked f double prime of x is equal to negative 4, which is concave down. Now concave down means this shape. We found a spot where the tangent line is horizontal in a region where the function has that shape, concave down, and that corresponds to a max. So that's our classic procedure for solving this type of problem. I want you to keep this in mind, that that's what the solution is. And the way we did it was we used the constraint in a direct way to rewrite the objective function, the function that we're trying to maximize. The method of Lagrange multipliers is an alternative strategy. And inside this course, we really don't get to experience why this strategy is so powerful. We're going to see it used only in situations where there's a single constraint, and only in situations where that constraint is called an equality constraint. So here it said that the total amount of fencing 2x plus 2y is equal to 60. This constraint can be rewritten as 2x plus y is less than or equal to 60, because we could use less fence. And then the process would be solved in a slightly different way. And the method of Lagrange multipliers allows that to be done in a very clean way. Multiple constraints would be, for example, if there were 3 variables here, and there was a connection between that third variable and the other variables. And we would then need some other additional information to have a meaningful solution. So it's kind of a letdown. We don't get to see how we will not get to see why this method is so powerful. But we'll introduce the basics, and that'll be enough. The basics, some vocabulary. The function that we're trying to maximize or minimize is called our objective function. The other piece of information inside the problem, inside the model, the resource limitation, is called the constraint. All constraints we're going to work with inside this course have the form g of x comma y is equal to 0. Those two ingredients are going to be enough to find the global max and or global min of the function. Together, the global max and global min are called the extrema of the function. So if you want another example of what we're doing, you might want to maximize profit at a factory or some type of other related setting. And what we've seen so far is to maximize profit, you would get a cost function, you get a revenue function, and then do profits equal to revenue minus cost. Take the derivative, set it to 0, there you go. But this idea of constrained optimization might be that maybe our model tells us to make this many of something. And in order to make that many, we're going to have to pay our costs up front. So I need to pay costs this week and I'll make associated sales next week. And the question is, do I have enough capital to do that? Do I have enough money to buy all those materials that the model suggests? So we would be safe if we build for example, our capital limitations as a constraint into our mathematical model to say this is how much money we have available to spend. And it might be the case that we spend all of it, and that this process will tell us that. So I put something, you can read it if you want, about plasma cutters, how much they cost, how many people you have to hire. So this paragraph here would indicate the type of resource limitation that you might face if you're trying to follow a maximization procedure. But it may not be realistic to follow that maximization procedure. You may have to scale back, and this method of Lagrange multipliers tells you by how much you have to scale back. So again, with the mountain idea, we're looking for the tallest mountain within 50 kilometers, not the tallest mountain anywhere on Earth. Or a more down-to-earth example, I guess both of these are down to earth. This is local. You want the cheapest gas, right? If you're filling up your car and one place has it 10 cents cheaper than the other, you're going to go there, unless that place is 2,000 kilometers away, or maybe 200 kilometers away, or maybe 20 kilometers away. There's some limit beyond which you won't drive to save 5 cents or 50 cents or $5 on gas. So this idea of constrained optimization is kind of building some more realistic components into our mathematical model. There's a limitation to how far we will go to maximize or minimize. So going back to this vocabulary of objective function being the thing we're trying to maximize and constraint being the limitations we have that we have to respect during this maximization or minimization process, what we will do in order to build both components into our model is we will skip over the matrix algebra, the linear algebra that kind of underpins some of this, and we'll go right to a formula. The formula is, first step, what we'll do is we'll construct something called a Lagrange function. If our objective function contains two variables, x and y, our Lagrange function will contain three variables, x, y, and this new weird squiggly thing called lambda. Lambda is called a Lagrange multiplier. In some contexts, lambda has actual meaning, like the value that we would have for lambda could be interpreted as something. But in most contexts, it's kind of a meaningless thing. It's there temporarily. We can find it if we want, but we truly don't need to know its value. Its only role is to help us incorporate the constraint into our objective function. What we do next is we take three partial derivatives. We take the partial derivative of this Lagrange function, which is denoted with a capital F. We take the derivative of that function with respect to x, with respect to y, and with respect to lambda. It turns out that one of these partial derivatives is going to be simple to calculate. It's always going to be equal to the constraint. Then we'll set the system equal to 0. That gives us a system with three equations and three unknowns, the three unknowns being x, y, and lambda. Solving the system can be very hard. 2 pages of work or more. It can be almost impossible to solve if it's a realistic model. Once we find all of our solutions, that gives us candidate locations for global max and global min on the boundary. What we do next is we take the xy coordinates of those critical points, if you want to call them that, and plug them into the objective function. So we're done with the constraint now. We don't look at the constraint. It doesn't matter what the constraint is equal, like the constraint's going to be equal to 0 at those points. We force that, but we're interested in what is the value of the objective function at those points. Maybe we have a whole bunch of them. We look at all those outputs and we rank them. The largest outputs are max, the lowest output is our min. If we only have one, then that's it. We'd have to pick up a random number or a random point, plug that into the objective function, and compare the two outputs to see if what we found was a max or if what we found was a global min. So that's step 5 is what I just described. It's the ranking process. Now I mentioned that we're not going to see this method in its full glory because we only have one constraint. We only have a constraint g of x, y, z is equal to 0. We only have equality constraints. We don't have inequality constraints. But we will see the extension of this Lagrange method to higher dimensions, to a 3-variable function, f of x, y, and z, subject to a constraint. And I didn't highlight this enough, that the constraint must be of the form g of x, y is equal to 0. Not g of x, y is equal to 1 or 2 or 3. Now this is really easy to fix. If your constraint's naturally given to you as something's equal to, let's say, 60 meters of fencing, all you have to do to make this fit the constraint is to subtract 60 from both sides. So you have the perimeter minus 60 is equal to 0. Now you've met the requirements to use this constraint optimization process. With 3 variables, x, y, and z, we construct our Lagrange function the same way as we do with 2 variables. The Lagrange function capital F is equal to our objective, little f, plus lambda times our constraint. We now calculate 4 partial derivatives, the x, the y, and the z partials, plus the lambda partial. The lambda partial will always be free. We don't have to actually calculate it. It'll be equal to our constraint. We'll see that in a second. This gives us 4 equations with 4 unknowns. It is generally not a very friendly system to solve, but once we solve it, we get our points, which are candidate locations for global max and global min. We plug those points into the objective function to see which point gives us the biggest output, which point gives us the smallest output. That ranking tells us which is the global max and which one is the global min. So it's a very mechanical process. That's one of the benefits of it. So we are truly doing a global max and global min solution process. This is not finding local max and local min. We're not finding the highest mountain. We're not finding the lowest valley. We're not doing anything with concavity. There's no diagnostic function, no capital D of x, y. So it's clean in that regard. I'll revisit the fence problem now and use this method, using this vocabulary. So our objective function, the thing we're trying to maximize, is area f of x, y is equal to x times y. Our constraint is how much fencing we have. We have x plus y plus x is equal to 60. That means 2x plus y is equal to 60. And this time I'm going to bring everything to the left-hand side. I'm going to subtract 60 from both sides. So it's 2x plus y minus 60 equals 0. Now it's in the correct format of the constraint. And I'm going to highlight that. The constraint is now in standard form. Okay, what we can do next is construct the Lagrange function. So capital F is equal to our objective function, little f, plus lambda times g. I'm not going to write all the brackets, x, y, and x, y, lambda, because it causes a lot of clutter. That's the only reason. It's very cluttered, and you don't have to write it either. Okay, so I'm going to plug in the objective function, x times y, and then the constraint, lambda times everything that's there. That whole thing on the left-hand side, that's all g. Don't put the 0, don't put the equal 0, just the left-hand side is called g. G of x, y is equal to 2x plus y minus 60. So we have 2x plus y minus 60. That's it. That's our Lagrange function. I'm going to multiply the lambda through the brackets. So capital F is equal to xy plus 2x lambda plus y lambda minus 60 lambda. Now we're going to do our partial derivatives. So capital F sub x, the x derivative of this function, we have the x derivative of x times y, which is just y times 1, plus the x derivative of 2x lambda, which is just 2 lambda, and the x derivative of the other two terms is 0 since there's no x in them. And then we set this equal to 0. Now for the y derivative of x times y is x, derivative of 2x lambda is 0, derivative of y lambda is y, and the derivative of 60 lambda is 0. We set that equal to 0, and then we do our lambda derivative. Look what happens when we do our lambda derivative. The first term doesn't contain any lambda, its lambda derivative is 0. The second term, 2 times x times lambda, well 2x is a constant as far as lambda is concerned, so we have 2x multiplied by the lambda derivative of lambda, so 2x times 1, just 2x, plus the lambda derivative of y times lambda, which is just y, and then the lambda derivative of 60 lambda, which is just 60. And we set that to 0, and our constraint fell out automatically when we took the lambda derivative of the Lagrange function. So I'm going to write down our system. Yeah, blank slide too. And I'll write down the system here, and we'll carry that with us to the next slide because there's not enough space to fully solve this here. We have y plus 2 lambda is equal to 0. We have x plus lambda is equal to 0. And we have 2x plus y minus 60 is equal to 0. Okay, so continued here. Y plus 2 lambda is equal to 0. X plus lambda is 0, and then 2x plus y minus 60 is equal to 0. Let me just double check those. 2x plus y minus 60, x plus lambda, y plus 2 lambda. Okay. So in the first equation, we could isolate for y, or we could isolate for lambda. In the second equation, we could isolate for x, or we could isolate for lambda. I'm going to isolate the first equation, or rather the second equation for lambda. Lambda is equal to negative x. And I'm going to plug that into the first equation. So we get y plus 2 times negative x is equal to 0. And that means y is equal to positive 2x. Now I'm going to take that, I'm going to plug that into the third equation. I'm going to replace the y with 2x. So we get 2x plus 2x minus 60 is equal to 0. So 4x is equal to 60. X is equal to 15. This should look familiar. Let's go back and get y. Y is equal to 2 times 15, which is 30. Thus, f of x comma y equals xy has a global extreme at 15 comma 30. Let's find out what that's equal to. F of 15 comma 30. What's the area that's fenced in? It's 15 times 30, which is 450, I think. 15 times 3 is 45, times 10 is 450. Now, how do we check if this is a max, a global max, global min? We could check our nearby number, plug in a different combination, like use 1 and 2, don't use all the fencing. Use 1 along the x direction and 2 along the y direction. We get 2, which is smaller. So we found the max. Now, this is okay, but technically, we really shouldn't be checking a point that doesn't match the constraint. So I'm going to go back and I'm going to fix that. Our constraint is 2x plus y minus 60 is equal to 0. So I'm going to change this 1, 2 to something else. We have 2x plus y equals 60. Y is equal to 60 minus 2x. We can pick anything we want for x as long as it fits this constraint. So I'm going to let x equal 1. That means y is equal to 58. So I'm going to check instead, I'm going to check 1 comma 58. And the area is going to be 1 times 58, which is smaller. It's 58. Definitely smaller than 450. So that selection matches the constraint. It uses all the fencing. We'll continue with more substantial examples in the next video. And a natural question before breaking is, why would we do this? Why would we do all this work to make that system of equations, solve it, and then concern ourselves with, did we actually find the max or min, and we're not checking concavity, when the alternative really isn't that bad. Like what we've already been doing for this type of fence question is much simpler. We just use the constraint to rewrite the function. And the answer to that, like why would we bother, is sometimes we can't use the constraint to reduce the function to be one variable. Sometimes we're stuck with a 2-variable function. And then this is in that case the best method.